Imagine a scenario where Earth's crust, which you might think of as a rigid and unchangeable shell, secretly repairs itself in mere hours after certain types of earthquakes. This fascinating phenomenon, recently uncovered through new scientific research, reveals that many subterranean cracks caused by silent or slow earthquakes can naturally mend very quickly, sometimes within a few hours, without leading to a major quake. And here's where it gets controversial. Could understanding these rapid healing processes change how we assess earthquake risks in the future? Specifically, this quick repair happens after what geologists call slow slip events. Unlike traditional earthquakes that release built-up stress suddenly and violently over seconds or minutes, or even hours in the case of the largest seismic events, slow slip events involve the gradual, steady movement along a fault line over days, weeks, or even months. These shifts are more subtle and less destructive but are key to understanding the full picture of tectonic activity. Thomas, a lead researcher in the study, explained to Live Science that both slow slip events and regular earthquakes can occur within the same fault system, but they generally happen at different depths and under differing physical conditions. The main factors influencing whether a fault slips slowly or suddenly are the fault's frictional properties and the effective stress, basically, how much force is holding the rocks together versus pushing them apart. The research focused on the Cascadia subduction zone, a major fault where the Juan de Fuca plate slips beneath North America. This zone is particularly well equipped for scientific study because it experiences frequent slow slip events and is monitored with advanced seismic networks, making it an outstanding natural laboratory. Cascadia's potential for destructive magnitude 8 or 9 earthquakes should not be underestimated. Interestingly, the study highlights that in these subduction zones, large, shallow earthquakes originate in cooler, less fluid-rich rocks, while the deeper regions, where slow slip usually occurs, are hotter, under higher pressure, and filled with fluids. This distinction is vital because it means that different physical conditions govern different parts of the fault. One especially intriguing finding is that in Cascadia, certain zones can rupture multiple times within a single slow slip event. This repeated activity suggests that stress is rapidly reloaded after each rupture and that the cracks managing these shifts can heal, or reseal themselves, remarkably fast. This fast healing process may allow parts of the fault to recover their strength and be reactivated quickly, multiple times during a single cycle. Such behavior was not fully understood before and represents a key puzzle the researchers aimed to solve. To observe how fast these processes could occur, scientists recreated deep earth conditions in a laboratory setting. They used a tiny capsule filled with powdered quartz and a trickle of water, mimicking the rocks and fluid conditions deep underground. By heating and pressurizing this capsule, up to 930 degrees Fahrenheit, about 500 degrees Celsius, and 10,000 times atmospheric pressure, they simulated the environment of deep fault zones. After just a few hours, microscopic analysis revealed that the quartz grains had welded together, indicating a significant strengthening of the mineral structure. This experiment illustrated that fault healing can happen quickly under the right temperature, pressure, and fluid conditions. Contrast this with shallow earthquakes, where healing can take years or even decades due to cooler temperatures and different environmental factors. These findings suggest that the fundamental process of crack healing operates at all depths, but the time required varies greatly depending on the environment. The other crucial aspect uncovered pertains to how stress rapidly reaccumulates in these deep faults. Cascadia experiences small, burst-like earthquakes triggered in quick succession, often aligning with ocean tide cycles, meaning the tides can indirectly influence when faults rupture again, just hours after they seem to have repaired themselves. This rapid re-strengthening might explain how parts of the deep fault can be repeatedly reactivated during a slow slip cycle. Understanding this fast healing and reactivation process isn't just an academic exercise, it has real implications for developing better earthquake models, especially in regions prone to major quakes. If fault repair mechanisms are included in predictive models, our ability to assess risk and monitor seismic activity could improve significantly. So, while these discoveries open exciting new avenues, they also provoke controversy and debate. Some experts argue that such rapid healing could mean our current understanding of earthquake cycles needs to be rethought. Others question whether these mechanisms are as universally applicable as the study suggests. What do you think? Could integrating fault healing into seismic risk assessments transform how we prepare for potential earthquakes? Or is this just another piece of a much more complex puzzle? Share your thoughts and join the conversation.